All right, now we are going to use the work energy theorem, which you have just learned about in Dr. Wu's previous video, to solve one of our problems. So starting off with this one, we've got a 6 kilogram block initially at rest. It's being pulled to the right along a frictionless horizontal surface by a constant force of 12 newtons, also directed in the horizontal direction. Find the block's speed after it has moved through a horizontal distance of 3 meters. All right, so I'm going to look at this again, trying to switch my mind physics gears, and we're going to look at this from an energy perspective. So if I start off, we always like to draw pictures of what's going on, so I'm going to start off by drawing kind of a diagram of the story. So we're starting off with a block with 0 velocity, and then later in the story, something like 3 meters later specifically, you can draw that in. There we go. So 3 meters later, we'd like to figure out how fast it's moving now. Ideally, when you pull something, it's going to start moving. So we're trying to get that speed. So looking at all of the forces that are in here, I'm going to draw all of the forces acting on my block, kind of like a little free body diagram on top of my picture. We've got our 12 Newton applied force going straight to the right. We would have the ground pushing up, so that'd be our normal force going straight up. And then we'd have the weight of the block, mg, going straight down. Okay. Now I know that my work energy theorem says that the total work is going to be the change in kinetic energy. Now ultimately, if we're trying to get velocity, that's kind of a hint to start thinking about kinetic energy, because we know velocity is hidden inside the kinetic energy equation, which we know kinetic energy is just 1/2 mv squared from the previous video. So if I think about what's applying work here, if I want to get the total work, I need to look at all of the forces that are acting on the object, but more importantly, in which direction those forces are going to be applied. All right, so now we're going to look at each individual force and look at which one of those is really providing a work for our story here, all right? And we know to get just individual work, we can, from one particular force, we can use that function FD cosine theta, okay? And what this comes from, this theta here, is an angle, but is basically an angle between where your force is applied or the direction that it's going, as well as what distance it's moving as well. So how do these guys compare to each other? Are they pointing in the same direction? Are they pointing opposite of each other? Is there some sort of an angle between them? That's this theta that we're referring to here, which you guys saw in the previous video. So I'm just going to do these one at a time, going in a clockwise direction, starting with our normal force. So if I look at this, if I have some normal force, I'll just call it N. And I know that the block is going to move a distance of 3 meters. So I'd have N times 3, right? And then as soon as I start thinking about this angle, how they relate to each other. If I have an object that's moving to the right, it's moving that way. And then I have a normal force that's pulling upwards. We can see that the angle between those is 90 degrees. So ideally, this force is not really in line with our direction at all. It's perpendicular to it. So this angle here is going to be the cosine of 90, which we know to be cosine of 90 is 0. So what this tells us is that these perpendicular forces here, perpendicular to our direction of motion, don't really have anything to do with the overall work in our story. Okay, so this is going to end up giving us this piece here. Ends up giving us 0. And that works for both the normal force and the gravitational force for the same reason. G would just be this way. Okay. All right. So let's look at the non-perpendicular force. Erase this real quick. All right, using the same exact principle with our 12 Newton force. Work is going to be, again, FD cosine theta. So my force is a constant 12 Newton force directed to the right. We move it a distance of 3 meters, so 12 times 3. And then I look at this angle again. I've got to see how they relate to each other. So if we think about this, the 12 newtons is going to the right. We are also moving the object to the right. So basically they're in the same direction. They're parallel to one another. So the angle between those is 0. There is no angle between them. They're going in the same direction. And we know that the cosine of 0 is 1. Okay? So what we find out here, once we've now taken a closer look at all of our forces, is that only one of these forces is providing the overall work that we're going to use in our work kinetic energy theorem. All right, from analyzing our forces, we discovered that this net work force, FD cosine theta, is really coming from just our 12 Newton force. So we'd have our 12 Newton force times 3 in distance, cosine of 0, which we know gives us 1. Okay. So I need to set that equal to, remembering the other side of the equation now, that this work is going to tell us about what our kinetic energy does. How does it change? So I know that 12 times 3 times 1 is going to have to equal the change in kinetic energy. Well, remember, a change in anything is just going to be the final thing, the final state, minus the initial state. So if it's a delta K, then we're looking at kinetic energy final minus kinetic energy initial. Delta K, there's the delta part, okay? So if I think about what these are, that's where I need to go back and look at the problem again. What are we really comparing? So if we start off with a block at rest, V equals 0, what is the initial kinetic energy? And hopefully you've decided in your head really quickly that that is 0. So our initial kinetic energy is going to be 0. And again, that's because it starts at rest. And then final kinetic energy, well, we know it's going to be moving over here. That's the speed that we're trying to figure out. So I'm just going to go ahead and leave this in terms of its variable form, since we don't know what that speed is. So I'm going to put 1/2 mv squared in here. So now we've applied, now we're comparing something numerical over here with work to something that will be numerical with kinetic energy. All right, so let's look at our numbers again that we're given and try to finish this thing up. So we know 12 times 3, cosine of 0 gives us 1. So 12 times 3 times 1, 36 equals 1/2. Wait, what was our mass again? It is 6 kilograms. 6 kilograms flat times the final velocity squared. So we can multiply by 2, cross multiply by 2, divide by 6, take the square root, and you end up getting a final velocity of just below 3.5. 3.46 meters per second. And there you have it. We have what started to look like a force problem, but we ended up looking at this with the work energy theorem and arriving at a similar result.